Well, you're still here. I mean, I tell this every year in every class. It's always the same. It's like the movie Real Genius, right? Because, you know, at the beginning, this is fun. After the class are all bright-eyed. It's full of the people in the lecture and the professors up there. And then, I mean, this is sort of a side gag in the whole movie. Then over time, there's like a few groups that are missing, and they're replaced by tape recorders, cassette recorders. So like, you know, and then like over time, there's more and more cassette recorders for students, and then the professor is just lecturing to the tape recorders. In the final scene, the professor's a tape recorder. So,
What movie is this?
It's called Real Genius.
Val Kilmer.
Val Kilmer's first movie.
Yeah, interesting.
Yeah, sad. You know, he was going to be the mayor of Santa Fe. All right. So, right, everybody, you know, projects are approved. They're hopefully chugging along, having fun. So the final assignment is due. We might talk about some of it today. I hope we have a little more time to talk about the assignment. We'll also have our usual problem session as well. All right, so last time we were talking about the fully quantum description of both the matter and the field. So we're looking now at both quantum matter and quantum field and their interaction. The fundamental theory of that, we're talking about magnetic field, is quantum electrodynamics, right? But this is an approximate version thereof. We call it quantum optical quantum electrodynamics, where we make a number of approximations. We're thinking about, first of all, low energy physics, so we're not thinking about particles being, electrons being annihilated or created. We are thinking about a situation where we're thinking about atoms or matter which has localized charge distribution, where we can make a multipole expansion, and the dominant term that we typically are keeping is the dipole, the interaction of the dipole with the field, so that's the dipole approximation. We might have to go to higher order multipoles if the dipole is 0 for the transition, but like typically we'll just leave it at that. And that we just, at the end of the day, reduce the whole description of the matter to 2 discrete energy levels of an atom. And moreover, we make the rotating ring approximation. So the 2-level atom approximation is a valid approximation. Both of these approximations are associated with resonance. They're both intimately related to the fact that there is a resonance between the field and the matter when the frequency of the photon is very close to these 2 levels. In which case, when there is a resonant interaction that's possible, that completely dominates everything, and we can ignore every other energy level in the system. Okay, so if we start, say, in the ground state, then if there's a resonant photon, it will be dominantly go into the excited state and no other levels. Or vice versa, as we'll discuss in the last few lectures, the problem of spontaneous emission, we haven't talked about yet, but we'll finally get to. If I start in the excited state, there's a resonant interaction which will cause me to decay to the ground state. So that, if there is a resonance there, and if we start our population in one or the other of these levels, we can restrict ourselves to those 2 levels. So that's where the 2-level approximation comes from, is resonance. And moreover, as we discussed last lecture, resonance also allows us to neglect the counter-rotating terms, the terms that are associated with things that look like virtual interactions, whereby we, you know, go to the ground state but emit a photon or vice versa, and neglecting those counter-rotating terms, again, was associated with resonance. Okay? So when we made all those approximations, you start with the Hamiltonian, you get this, okay? Which is the Hamiltonian of the matter, which is my two-level atom, the Hamiltonian of the field, which is a bunch of harmonic oscillators, and the interaction Hamiltonian, where this constant is the dipole energy interaction between the field and the mode, which has some energy of the photon. So this is looks like the Rabi frequency, right, that we had classically. The Rabi frequency that we had classically was the dipole interaction energy. When I say the frequency and the energy, there's always an H bar that goes between them. So when I say the Rabi frequency and I say the energy, I mean H bar times that. Is the dipole interacting with the field, right? And the field here is the field associated with sort of one photon in that mode. Okay? We'll come back to that in a moment to remind ourselves. Okay? So that's our starting point when we're thinking in quantum optics about the atom-field interaction. This is the standard Hamiltonian. Okay? Now we're talking about the simple case of a two-level atom plus a single mode of the field. That situation, thinking about that, is what's known as the Jaynes-Cummings model, which is an incredibly important model in quantum optics and the foundation of pretty much all of quantum. Interestingly, I'm sure Jaynes wouldn't have been wildest dreams about that. So the Jaynes-Cummings model is a model of what we call cavity quantum electrodynamics, cavity QED. So it's a relevant model to describe the situation where we have, for example, an optical cavity, which say a Fabry-Perot cavity, which has some modes in it that, and the spectrum of modes, we have some discrete spectrum of modes associated with the boundary conditions, and we have aligned the mirrors in such a way that there is some mode of the cavity at some frequency, I'll call omega sub c, some particular cavity mode that is tuned to be right near the energy associated with this resonance. Okay, so we've tuned the cavity so that there's one cavity mode that is right near resonance, almost on resonance, and the other ones are so far from resonance I can completely ignore them. So for that one particularly cavity mode that is specified by, its polarization and everything else, we can say there's one mode. Okay, so that's the Jaynes-Cummings model, which is applicable to this physical situation. I mean, Jaynes and Cummings they didn't really think about this, but then people said, well, let's actually make a system that they were just wanting to look at its properties mathematically. But then later, people engineered the physics that physics is actually well described by this toy model. Okay, and so under that circumstance, if we have one mode, we just call that mode has some frequency. So the Jaynes-Cummings Hamiltonian, and I'll no longer label the modes. This annihilation operator are the creation and annihilation operator for that mode. Okay, I'm not putting it was only one mode, so I don't have to label it by anything else. And then I have the energy of the atom. And this is the projector on the excited state with the ground state at zero energy. And then I have H bar G A plus H bar G A minus, where I'll take the G's. This real is going to be EG dotted into the cavity at the position of the atom, square root of H bar. And this I'll just take it to be a real function, say a standing wave. I don't have to, I can have the complex non-case, but I'm just not going to drag them around. Okay. All right, so this is the Jaynes-Cummings Hamiltonian, and as we discussed last lecture, we can easily diagonalize this system and find the eigenstates of the whole system that involve both the field and the atom. Okay? They're the moral equivalent of the dress states when we looked at the eigenstates with the classical field. Okay, but they're now dressed by photons. And the reason we can easily diagonalize this is that this thing commutes with the total number of excitations in the system. So the total number of excitations I'm calling the number of photons, it's the number operator, plus the number of in the excited state, the projector on the excited state. So because of the rotating wave approximation, we conserve excitation number. If the atom goes up, the photon is lost. If the atom goes down, then we create a photon. So the total number of excitations as measured this way, and you can do the commutation yourself, it's zero. And because of that, a good quantum number for the system is the number of excitations. And if we look at a basis for the Hilbert space, our basis for the Hilbert space is the tensor product of the basis states for the atom and for the field. That's a basis for the whole Hilbert space. It's infinite dimensional. It's 2 times infinity, which is still infinity. But this Hamiltonian is block diagonal in the total number of excitations, right? So I can write, if I write this as a matrix, there's a one-dimensional, then there's a 2 by 2, and another 2 by 2, and another 2 by 2. This is a 1 by 1, this is a 2 by 2, everybody else 2 by 2. Where I'll call each of these guys, this is H1, H2, dot, 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 Hn, where this is the Hamiltonian matrix in the subspace associated with n excitations. Okay? So the basis, if I have n excitations in the combination of the matter and the field, then either I have n photons and the atom in the ground state, or I have one less photon in the atom excited state. So these two states have n excitations by this definition. Okay, not n photons, but n excitations. Those excitations could be in the matter or in the field. And when written, when I then look at my Hamiltonian in this subspace, okay, so I write down the matrix elements of that, then the Hamiltonian in that subspace can be written as I'm calling spin up, because this is a 2 by 2 Hamiltonian, I can think about this as a pseudo spin. Okay, it's just a qubit. So there's another sense in which I have a qubit that's different from our original 2-level atom. Now I'm including the photon in my description of this. So this is my up and down, and I'm calling sigma 1, it's like sigma x. And sigma 3 is like sigma z. Everyone clear what I'm doing? Yes?
So we're sort of consolidating excitations in both the field and the matter. I might just be grasping at straws here. But is this at all similar to how we
Yeah, they're the same thing.
do the same thing?
It's the same thing. So you can think about a polariton as dressed as matter dressed by fields. But polaritons are more general objects than this because we're thinking about general current. But a polariton is a fancy thing for saying addressed excitation of both the matter and the field together. Yep. Yes. Omega, thank you for, so delta is the difference between the cavity, that's the definition. Okay. So, and this omega sub n here is defined to be equal to, or h bar times that is equal to h bar times the square root of n times 2g. So that's what we found last time. Okay. So, what does omega n mean? Omega sub n is the Rabi frequency associated, this is our familiar Rabi Hamiltonian, just like we had before with the when we thought about the classical field, where we had the detuning and the Rabi frequency. There, the Rabi frequency was the dipole dotted into the strength of the classical amplitude of the laser. Here, there's going to be a discrete Rabi frequency that's different in each of these sectors for different numbers of excitations. For every number of excitations, I have a different Rabi frequency. Why? Well, if I have more photons, I have more electric field. But now the strength of the electric field, so to speak, is quantized. The energy is quantized, so I have a discrete Rabi frequency depending on exactly the number of quanta. So if I were to write this out over here again, let's just, for the moment, let's suppose this were a plane wave. Then it wouldn't be real, but who cares? It's really got it, right? I just want to put in what this is. This thing is equal to h bar times g times that would be equal to minus, well, there's some polarization. D dot E dotted into the polarization of the mode times the square root of 8 pi n h bar omega c over d. Okay, if I put this square root of n inside here, and then the 2 gives me a 4, and I get that, right? Is this what you expect? What is inside here? Well, this is the energy density associated with n photons. N times h bar omega is the energy density. How is the energy density in the field related to the strength of the electric field? Now, those of you, I'm going to turn around, those of you who took final 11 with me should remember the relationship between energy density and the strength of the electric field. E squared over 8 pi. So the energy density is E squared over 8 pi. And if the energy density is equal to n photons in this volume, then you get the strength rah. This is nothing more than what we would expect. Given that number of photons, that's the strength of the field, and that strength of that field interacts with the dipole, and that determines the Rabi frequency, which is the rate at which energy is exchanged between the matter and photon. Awesome. All right, so given that, we can find the eigenvalues and eigenvectors in a snap, in a flash. We can just look at this and we can know what the energy eigenvalues and eigenvectors are. What are they going to be? There's going to be two of them, because it's a 2x2 matrix. I'll label them plus and minus for the n excitations, and they are equal to n times the energy in the photons in the cavity minus h bar delta over 2 plus or minus what? Right. Okay, so this is equal to h bar omega over 2, the square root of omega n squared plus delta squared. Just like we had when we had the classical Rabi frequency, but now in this, we have this discrete Rabi frequency associated with that sector. Yeah?
Why shouldn't our detuning test as well? Like,
We have one frequency.
only one frequency.
We're only talking about one mode of the cavity. We can have a different number of photons, but they all have the same frequency. The photons all have this frequency. Okay. If we had different frequencies, we had different detunings. So we're not having different, we have one frequency, but we have different amount of energy in the system. Yeah.
Is the number of photons limited somehow by the frequency and G? Because Tuesday you said that the energy levels never cross over, but
Yeah, so we are always, we must have G much smaller than omega c, and as well as the G. So this was what we also had in, or I can call it omega sub n. This was what we said when we talked about things classically as well. I might have a optical frequency at 100 terahertz, and that's this, but I'm detuned by some maybe gigahertz, megahertz, kilohertz. So my detuning is tiny compared to that, and my strength of my interaction is tiny as well compared to that. This might be megahertz, and this might be 10 to the 15 hertz. So that was implicit, and we continue that. Yeah.
It's a bit surprising that omega is not linear or not harmonic, that as we increase n, it doesn't increase the same relative amount as we go on.
Yeah, well, that's just, I don't know if that's should be expected, because the interaction strength depends on not the intensity, but the electric field. The electric field goes up linearly with n, but the electric field goes square root of n. Did I say, what I meant to say is that the intensity goes up with n, but the electric field goes up like the square root.
Okay.
So it's because that's what determines the strength of the D dot E is what determines the strength of the interaction. But yeah, it's the square root. It is interesting. Right. So those are the energy eigenvalues, and that spectrum is what's known as the Jaynes-Cummings ladder. Okay. So what we drew at the end of last lecture, I'll redraw again, is just a picture of the spectrum. This is energy, and if we are, let's just start for the case where I'm exactly on resonance, okay, where the cavity's tuned to be exactly on resonance with the resonance of the two-level atom. Then we have a spectrum which is harmonic, as Donald might have expected. So this is the n equals 0 case, this is the n equals 1, n here is the number of excitations, not the number of photons. Maybe I'll call it capital N to not, otherwise it's confusing. Okay, so this, I should have done that before. Little n is the number of photons, big N is the number of excitations. I'm sorry?
You realize most of us are going into a static exam for n also means something else.
Well, you know, it's all about context.
Or Z or Q.
It's all about context. Okay? This guy is just the ground state with no photons. This guy is either the ground state with one photon or the excited state with no photons. This guy is the ground state with 2 photons or the excited state with 1 photon, ... The one we said that had, this guy has n equals n, e minus 1. Right, so these are doubly degenerate when we are in resonance. Okay? But when I turn on the coupling, this is where I have delta equals 0 and G equals 0. Okay, or makes N equals 0. Now I turn on the interaction and my states split out. Okay. This splitting, this is harmonic. Each one of these guys is split by cavity when I'm right on resonance. Okay. And now when I turn on the interaction, what happens? This guy stays fine, but this guy splits into 2 eigenstates, the plus and minus states, right? So there's a state here, and this guy gets split as well. I'm not drawing this to scale. These guys are way, this is huge compared to this, but I don't have enough room, so these guys are never going to cross. Okay, and then there's this guy up here, and it gets split by some amount. What is the splitting here? The splitting here is the splitting between these 2 modes, and when delta is equal to 0, this is equal to h bar over 2 plus minus over 2 n times 2g. Right? That's what that is when delta is 0. And so this guy goes up by 2g, this guy goes down by 2g, and so this splitting is 2g times h bar. For the first one. For this guy, the splitting is h bar times the square root of 2 times 2g. And this splitting is h bar times the square root of n times 2g. Yes?
So as the number of photons in the field increases, I get stronger and stronger splitting. Should I think of that as like, oh, essentially the electric field that's producing my atoms just becoming stronger?
Exactly. So it's exactly this fact. And it's the fact that it's quite interesting. In the absolute interaction, this is like a harmonic oscillator. We have a linear separation, an equal separation from all the energons. But when I look at these states, the eigenstates, we call the dress states, or the polaritons, then we can have a nonlinear ladder. That's very important in our ability to control them, to restrict our attention. So this is the state plus with 1 photon, and this is the state minus, or with 1 excitation, with 1 excitation. This is the state plus with n excitations. This is the state minus with n excitations. Okay. So these are the eigenvalues, these are the eigenvectors. The eigenvectors are the eigenvectors of the whole Hamiltonian. They have both matter and field character together. Yes, Lee?
So because of that restriction, delta crossover, could we get to a point where
Well, if we go to a high enough end, then eventually they would cross, okay? But that would violate our assumptions, right? Because then omega sub n would start to get the order. So mathematically, yes, it can happen, but almost never do we worry about that, because we would need to have, in that case, some kind of super high intensity excimer laser with so much power in it that so many other approximations break down at that point that it wouldn't make sense. So yes, mathematically we can worry about that, but physically we never do, because we never have that big a number of photons that would correspond to so much energy that everything else would break down in our approximations.
Is there no like violation of like no level crossing at zero? No, that won't.
Yeah, no, I mean levels cross. They would have to then ask them. Then they would have to mix. In that sense. I mean, the rotating wave approximation would break down at that point. Okay, and then they would mix. Good. All right. I just wanted to let's look at what this thing looks like for a non-zero change. Okay. So let's just say, for example, the tuning was negative. Okay. So then I go back to this Hamiltonian here in the absence of, if I look when there's no interaction term here, then this is n h bar omega over c minus delta projection on the excited state. That's what my Hamiltonian is. This is times the identity operator. So what is the energy levels? What do they look like? Well, firstly, again, I still have, as before, the case where I have the ground state with 0 photons. But now, because I don't have the same energy in the photon as I do in the atom, because they don't have the same energy, if I have a photon, it has less energy than the atom does, because I'm ready to. Okay? So what I would have then is, if I put in 1 photon, that goes up by h c. But then if I have the thing in the atom, if the atom now has more energy, so I'm ready to. Okay, so this guy is that splitting this delta. Everyone clear on that? And this distance is h bar delta, is h bar omega c. So here I put in 1 excitation. If I absorb the excitation, there's more energy because it's ready to. Okay. And then I would go up another rung of the ladder by putting another photon over here. This would be G with 2 photons, or E with 1 photon. Again, the splitting here is delta. And up the ladder. Okay. And now if I turn on the interaction, this is where the interaction is 0. Again, this guy stays the same, and these would be split. And these guys would get split. Where the splitting now here is equal to h bar times the square root of delta squared plus 2g squared. That's for n equals 1. And this splitting is h bar squared delta squared times 2. And up the ladder. When g is 0, they're split by the detuning. When g is non-zero, I get this additional splitting, but the amount of splitting depends on the number of excitations. So it's not the same splitting. Again, I have a nonlinear ladder. Okay. And up the chain. What are the eigenvectors of this Hamiltonian? If I look at this guy, those are the bare, so in the absence of the interaction, these are the eigenvectors. We call these the bare states. They're naked. They're bare.
So we need to address them.
We need to dress them, right? So what are those eigenvectors? How do I find the eigenvectors of that operator? You could do that, be my guest. Exactly. At the end of the day, on the pseudosphere, there's a block sphere here. This Hamiltonian has an associated omega effective for the nth guy, which has a z component or a 3 component and a 1 component. If I think about this as a Cartesian coordinate system of 2 should be in this right hand, right? And so this is my omega effective, right? If I have a Hamiltonian, which is, or an operator which is h bar omega effective over 2 dotted into the these Paulis now are associated with these guys, then what are the eigenvectors of this system? They're spin up and spin down along the direction of this thing, right? So the eigenvectors plus n is equal to spin up along this, but spin up along this, the direction of this vector is the vector over its, right? So this thing is in the, if I think about it in terms of the coordinates, then this is equal to cosine theta sub n over 2. Spin up is e n minus 1 plus sine theta n over 2 g n. And minus n is equal to cosine theta n over 2 spin up minus sine. I'm sorry. Yes. Thank you.
You also want to do the I5.
Phi is 0 here because I've taken g to be real. But thank you. Right? So these are the dress states. They involve both matter and field quantity, where the theta sub n is the direction of this angle, which is, if I look at that, that's the tangent of the theta of n is equal to the omega sub n over minus delta. Okay. Just doing the trigonometry. It has a minus delta component, a theta sub n component. This is the geometry. Yeah, you can do the determinant. You should learn how to do this. And so, in particular, when delta is equal to 0, what is theta sub n? Pi over 2. And when theta is pi over 2, then I have cosine of pi over 4, which is 1 over root 2. So, and sine of pi over 4, which is 1 over 2. So in that case, I have the equal superpositions of the symmetric and asymmetric combinations of those guys. Okay. Interesting. All right. So now let's think about, this is what all I did here is, I said, this is the Hamiltonian, the Jaynes-Cummings Hamiltonian, and we diagonalized it. We found the eigenvectors and eigenvectors. given that, we can think about dynamics. We can think about dynamics lots of different ways, but let's think about this. So let's suppose, for example, I prepared the system at time t equals 0 in the excited state, no photons in the cavity. Okay? So let's say I were able to do that. What would happen at a later time? So in this case, this guy has n equals 1 excitation. That excitation in this case is in, and let's suppose that I'm on resonance. Okay. I Rabi oscillate between what two states? And the ground one. So the state at a later time, which is e to the minus I, is our usual rotation on the Bloch sphere. But the Bloch sphere now is this Bloch sphere, which has both atom and photon character together. And so this is going to be equal to cosine for 1 excitation over 2 times theta sub 1 here is equal to 2g. Okay, so that phase then is n times square root of n times 2g. So what this would mean is that if I had this guy and I somehow was able to shine a laser from the side of the cavity, put a pi pulse in there, and put it in the excited state and said, what's going to happen is, I've made this resonant with some mode. It would then, it would go to that with 1 photon in the mode, and then back, and it would just keep going while you oscillate. It would emit the photon into the mode, and then it would reabsorb it, but in a coherent way, in a way that corresponds to a Rabi oscillation. So if I chose omega 1t to be equal to pi, and then somehow I stopped it, then the state at that time would be what? It would be this, with that phase, which I really don't care about. But what I would do is I put the atom in the cavity and I have 1 photon in the mode. I would do exactly that. And that's a way of dumping exactly 1 photon into the cavity if I could do that. I can exactly dump that photon into the cavity. Okay. And vice versa. I could transfer it back and forth. Okay. These are known as vacuum Rabi oscillations. It's not really means 1 excitation Rabi oscillation. It's called vacuum Rabi oscillation because I started the system in the vacuum. Okay, and then I emitted that 1 photon, and I Rabi oscillated back and forth. But it's a 1 photon Rabi oscillation, okay, or 1 excitation Rabi oscillation. Yes, sir. Yeah, I could. In principle, I could, if I could create that 1 photon, I could dump exactly 1 photon into that cavity and then store it and then pop it out. It's not, those of you who are at Alex Fisher's Jaynes exam, was that yesterday? Lord. God, it was much more complicated to create those single photons. This is a much easier way, but but this is done with atoms. It's not done, in the solid state. This is a whole other story. Yeah.
So I think I'm getting lost here a little bit. We have E and E
some number of
How
photons.
about some number of photons in a predetermined,
Mode.
yeah, one mode.
There's one mode
Is
and we
there-
have some number of excitations.
Is there, we're also driving it with some sort of laser that's causing?
No, I'm not. I just made another thing, said how could I create this?
Okay, so we just have.
I mean, mathematically, this is my initial state. Physically, I might shoot another laser from the side of this cavity and do classical pi pulse to put it up there.
So it's just hanging out in this cavity.
It's in a
oscillating.
tweezer, it's in a trap, it's fixed in space,
Yeah.
and it's located at some position that determines the strength of G.
We
Go
are,
on.
we don't, like, it's just the atom, we just have our atom and our one photon or not, depending on.
That's correct.
And we're obviously in between them anyways, that way.
And we rob the and the only state that is coupled to this state is this one. And this would, in principle, just rob the oscillate forever. Yes?
You said so we're going back and forth between the excited and ground signal.
Yeah.
Is this because of our quantization of the rabbi frequency?
Well, the value of this is because of it is determined by the discrete nature. But the fact that it's just Rabi oscillates like this, I mean, this would be true classically as well. If I shined a laser on an atom, it would just it would just Rabi oscillate in principle if my system is described by that Hamiltonian. But now I come to a point. Of course, this isn't what happens in the real world. This would say this thing would go on forever. It would emit the photon, absorb the photon, emit the photon, and it would Rabi oscillate like that forever. There's nothing. This is what this equation tells us. But physically, that's not what actually happens. Why not? Yes, that's one reason. So in this case, we're assuming that the only mode into which this photon can emit is the cavity mode. There are other modes that have the same frequency into which the atom can also emit. And it can emit out of the cavity with some spontaneous emission rate corresponding to emission of another photon. Yeah.
We're also assuming that one, we only have one photon, and two, we know we only have one photon.
Well, this is not so terrible. It's not that we have one photon, we have one atom. And we had the vacuum. That's pretty easy. That's fine. I mean, if there was actual temperature, we'd have to ask, are there photons in the black body at that, at that frequency? If we're in an optical frequency, we're fine. I don't have to worry about that. So this is not a bad approximation, but we are assuming in our system that G is much, much bigger than gamma. This is saying the rate at which this is happening, the rate at which it emits into the cavity mode is huge compared to the rate at which it emits. And that's, related to, in this case, the volume. We need to have the mode volume sufficiently small so that the electric field strength is really high, right? At least one thing about optical frequencies. There's another thing that's totally not true in the real world that I assumed. Let me just finish some more. You have an idea?
Yeah.
Yeah, go on.
On Tuesday, you said if we have perfect pictures.
Yes, absolutely. Yes, indeed. So this picture ain't exactly right. The actual spectrum is one in which these things have a finite line width, which we typically call kappa. Kappa is the rate at which the photons might leak out of the cavity, because this has a finite reflectivity, or it might be absorbed into the cavity mirrors just by phonons. It's not a perfect cavity. So I also want G to be huge compared to kappa. So this description is what we call a closed quantum system, where the only degrees of freedom was this one mode and the atom. And it's a very closed set of degrees of freedom, and they're coupled, and you have energy that sloshes back and forth between them. But really, we have an open quantum system, which is to say, there are many, many, many other modes that are actually coupled to this atom resonantly. They're all the plane wave modes that have the same resonant frequency or near resonance, but they're propagating, and they're also coupled to the atom. And the atom can emit into them. Okay? So the whole story for decades of cavity 3D was trying to achieve this, and there's various parameterizations. Often we can think about the vacuum Raman frequency. Say we often think about this squared over this as some parameter that is typically called cooperativity. And we want this to be huge to do cavity QED, which involves making the mirrors really, really good. Boy, those dielectric coatings, they had improved over time, and people worked on that like a dog to make that better and to stabilize the cavities and think about what kinds of to make these things. Now the other thing that's important here is what determines G. Let's again say that H bar G here was B dot E dot polarization, the square root of 2 pi, and we elucidates this. So how can I make G bigger? I could try to make V smaller, right? People did. Jeff Kimball is one of the greats, sadly passed away recently. We knew him quite well, a good friend. Was a pioneer in cavity QED, whose lab worked forever to make V as small as possible. Bring these cavities, mirrors together as tiny so that a femtometer movement of them didn't affect it. Make V smaller, we'll make this. What else can I do?
Stronger dipole.
What's that?
Stronger dipole.
Stronger dipole, right? So I can think about how do I make the dipole moment bigger? The dipole moment vector depends on the matrix element of these guys. And that dipole matrix element here, this is the charge of the electron. E means something else now. This is the charge of the electron times the position of the electron relative to the nucleus, right? So it depends on this matrix element. So some of the most, maybe I'll switch on to my work in doing this kind of experiments in cavity QED was multifold advances, and one of them was instead of thinking about an optical transition, so typically this thing is typically for, if I'm in the ground state of the atom, if this is the true ground state, then this thing is on the order of the Bohr radius. It's on the order of a few angstroms. Okay? Not a very big electric dipole moment. That's how big the wave function is if I think about near ground state. And so my dipole matrix element in that case is on the order of, but I don't have to restrict myself to the true ground state. I can go up to a higher principal quantum number. And when I go to a higher principal quantum number, the radius of the atom grows very rapidly. it grows like the square of the principal quantum number. And when I go to very high principal quantum numbers on the order of 50, those states are known as Rydberg states. And so some of the real pioneering experiments in cavity, or additional experiments in cavity 2D, were done particularly by the group of Serge Roche, who worked for which he won the Nobel Prize in 2012. And I'll tell you a little bit about that now, and some of which you're going to study in your homework, and some of you are going to write a Wikipedia page about this. All right. So the Jaynes-Cummings model here so this is sort of the typical kind of optical configuration. This is where, you know, I have some kind of ferrochrome mirror, or these guys are going to trap an atom in here. But an alternative was work that was done in the group of Serge Roche in Paris, where instead of thinking about an optical cavity, they thought about a cavity with superconducting mirrors where they have incredibly good reflectivity. And you can do that in the electronic regime, where instead of this being a cavity that's separated by, half a micron, it's separated by some centimeters. This is a microwave cavity, okay? And now I'm resonant not with the ground state to excited state. My spectrum looks like this, and these two levels, there are two levels here, which say I have n equals 52 and n equals 52s and 52p are two levels here that are separated by some few gigahertz rather than hundreds of terahertz. Okay, these states are incredibly long-lived. Their lifetime is incredibly long compared to the first excited state. The spontaneous emission rate is tiny. The cavities have very, very high reflectivity. A capillary is very, very, very small. And moreover, my dipole matrix element is huge, because the radius of the atom, the radius of the electron is so far, I can have huge electric moments. And so this was, you should read about this. These have very high cavity breakdown times, high cavity Qs, etc., etc. Now, interestingly, in the modern world, circa 2010 plus, Rydberg atoms, sure, they have a big radius, but you know what has a bigger radius? Something which is a macroscopic chunk of material that can be like an antenna. And the idea of turning this from, instead of thinking about my, an actual atom with energy levels, I have a artificial atom, which is related to a nonlinear harmonic oscillator of a superconducting circuit. And we can talk, I can tell you a little bit more about that. I just want to get some of the basic points here. The basic point of this is that I have this thing here, which is a chunk of material that is in contact with a cavity of microwaves again. Instead of having my two levels be two levels of an atom, I have two levels of the current, the quantized current flowing in this material. Okay? And in fact, in the modern experiments that are done, they were really pioneered by the group at Yale The ideas, Steve Gervin, this is what's known as circuit QED, which is the same thing as cavity QED, but now where my atoms are superconducting circuits. So this involves Steve Gervin as a theorist, and Michel Devereux, who recently won the Nobel Prize this year for earlier work he did on macroscopic tunneling in superconductors, and Rob Schlokoff. Something like that, I forget how I'm supposed to say. So in these labs, they're actually looking at this thing here, and you see there's a Joseph junction, but then there's these huge panels. This thing is an antenna, which had, many microns long, almost centimeters long. You can have a huge electric dipole moment here. So huge in this problem. That you even can break down the rotating wave approximation in the system, your GQV. And in this, let's see. So this is already an old chart. I have to go back and I should update it. God knows when I did this a few years ago. Let's say 4 years ago, maybe 6. You can see the size of these things, right? Here's the dipole moment in units of the Bohr radius. For an atom, it's 1. For the Rydberg atoms, it's 1,000 times here. Now it's 20,000. I'm sure it's even bigger than this. Right? And then we can look at the things like the ratios. This is 1 over the cooperativity of what I call it. So, and again, smaller is better here. It's 1 over it. And this is 2 orders of magnitude better. So if you're really this kind of exploring this cavity QED, things that, as a graduate student, I said, there were always these crazy papers. Let's imagine it's Hamiltonian, and we just do all these things. And we always say, what are you talking about? This is, fantasy. This is never going to be anything. We live in the real world. But it just goes to show you never know what can actually be done in the real. And things that were just completely nuts from my perspective in 1990 are now routine in these circuit QED experiments. All right. Excellent. Okay, so maybe there's next thing I want to talk about, maybe 2 more depending on our time, is so the way these superconducting coupled to a microwave cavity, superconducting transphons coupled to a cavity work is not exactly in the regime that we've talked about, where we have things like vacuum-Rabi oscillations. They're operated in a regime where the magnitude of the tuning is huge compared to the Rabi frequency. Okay, so I'm very far from resonance. So I want to just talk briefly, this is also related to your homework, about cavity QED in what's called the dispersive regime. What do I mean by that? Let's assume that the size of the detuning is absolutely huge compared to whatever Rabi frequencies I care about for whatever angle. In that case, well, if I can think about my 2-level system and some number of photons are going to, I'm not going to excite the system, right? I'm very far from resonance. But nonetheless, the effect of the coupling of the photons to the atoms and the atoms to the photons, they're going to affect each other. And we want to get an approximate description in this. how should we do that? The way to do that is we can, for example, look at the eigenvectors and eigenvalues of the system in this approximation when the tuning is big compared to that. So let's look at these eigenvalues, for example. If I look at the eigenvalues of the system in this limit, I'm going to say this is huge compared to this. So I'm going to do a Taylor series expansion. I'm going to bring the sigma squared outside the square root. The square root of sigma squared is the absolute value of that sigma. Delta times the square root of 1 plus omega n squared over delta squared. Okay? Just taking that outside the square root. Now if this is small, this is approximately equal to 1 plus omega n squared over 2. Right? So what this then equals is n omega squared minus delta over 2 plus or minus the absolute value of that plus or minus.
Square root is, sorry, approximately for that. Should we have done something?
It should. Sorry, excuse me. Absolutely. H bar omega over 4 omega n squared over the absolute value of delta. Okay. And this thing over here is equal to n times 4g squared. Omega sub n was the square root of n times 2g. So this whole thing I'm going to write as h bar chi, where chi is g squared over the magnitude of that times n. So those are the eigenvalues. The eigenvectors, I also have to think about approximating them, right? The eigenvectors in this case are, if I think about this first, remember theta is a small parameter now, because this tangent of this theta is that. So when this is huge, theta is very small, and cosine to first order is 1, and the excited state, this is omega sub n over 2, that's minus over 2 delta g comma n, and vice versa. So this is like first order perturbation theory. These are the bare states. And the bare states are perturbed to this order. Okay? This, of course, is equal to the square root of n times 2g. Okay. But I want to just get to the point here without going through all the algebra. I need to write this down and put this in my notes. I will do it. But now what I want to do is let's just look at the Hamiltonian, which I'm going to write. So this is the exact Hamiltonian. These are its eigenvalues. And now I put in these approximations, right? So I'm going to expand the eigenvalues to lowest order. I get this thing. I'm going to expand the eigenvectors to this order. So these are the eigenvalues, these are the eigenvectors, and now I plug them in. Yeah, Nate.
Should the absolute value of delta?
No, this is the this is delta. Yeah, yeah. Okay, so when I plug all that in and do all the algebra, which is very tedious, I get the following. Let's take a look at this. Where did this come from? Let's come back to the eigenvalues here. What we see here is eigenvalues that go up or down by an amount proportional to n. So if there's a spin up state that depends on n and a spin down state. Okay. So that's where this is coming from. What is happening when we are far detuned, when we're not on resonance? What do we expect to happen? As we said, if I had my two-level system, G and E, and I put on light that's far from resonance, what's going to happen? I'm not going to get very much excitation, but I'm going to get a light shift. The energy level is going to be shifted, and the amount that's going to be shifted is that energy eigenvalue, and this state is slightly dressed. It has some tiny amount of excitement in it, right? I've dressed the system. I'm not causing excitation to go from the ground state to the excited state, but I'm causing the energy level to shift. That, and the light shift classically depends on the intensity. What is happening here? Well, what we see is, firstly, I get a slight shift in the energy. This is the effect of what we call the Lamb shift. The energy of the ground state is shifted by an amount that depends on its coupling to the vacuum. That's fine. But what does this do? What this says is that the two energy levels of the atom, E or G, get shifted up or down depending on the number of photons. Okay? So if there are n photons in the cavity, the ground state will go down by some amount and the excited state will go up. But that's what we expect classically. But now we have a quantized light shift. The amount of shift depends on the discrete number of photons. If I have a different number of photons, I have a different light shift. Or vice versa. I could say that I have a phase shift on the photons that depends upon whether so remember, A dagger A is the rotation on phase space. It tells me how fast this is rotating. This is saying because there's material in the cavity, I have an index of refraction, so I change my rotation rate. But my rotation rate depends on whether I'm in the excited state or the ground state. So I write information onto the photon depending on the state of the atom. So what's interesting about this, and you will study in your homework, is this is a way in which, for example, I can measure how many photons are in the cavity without absorbing the photons. Because this interaction doesn't change the number of photons. It just is going to give me an energy level shift on the atoms depending. And how do I measure that energy level shift? I measure that energy level shift by measuring how much phase is accumulated on the atom wave function. And if I'm going to have a different phase shift on the atom depending on the number of photons. And how do I measure the phase shift on the atom? In a Ramsey interferometer. So that's what Harosh did. And that's what you'll study. And they measure, they can measure by looking at a Ramsey interferometer and seeing a discrete different number, different phases, the phase shift will depend on N. And that kind of measurement is known as a quantum non-demolition measurement, a QME measurement. So it's a way, it's such a cool experiment. So you're measuring the discrete light shift, right? The light shift is an energy shift. The energy shift turns into a phase shift. We measure the phase shift in a Ramsey interferometer. But now that energy level shift, the light shift on the atom is discretized. It's discretized. Go. All right. Bye, everybody. See ya.